The next, I guess it's just two slides I have here, are about something called the exponential probability density function. You have actually seen this before when we were introducing some of the chapter 4 concepts. Now we're going to actually put a name to this distribution. And the exponential distribution, and a random variable that has the exponential distribution, it comes about when we are looking at consecutive events or successive events of a Poisson process. Now, this isn't really something that you need to know, but if you are an industrial engineer or an engineering management major, you will actually come across this. There's a relationship between the exponential distribution and the Poisson distribution. So I'm kind of planting a little seed there, I guess. So this is what the probability density function of X looks like. It has this parameter lambda, and that is something that is always bigger than 0. And it is an exponential decay function. I usually like to write this as X bigger than 0, but we also know we could write that as X bigger than or equal to 0. A plot of this PDF, so if this is X and this is 0 and this is the PDF, remember it's a continuous random variable here. There's no commas in the range. It looks like this, and it goes on forever. It's theoretical, so we put 3 dots there to show that it goes on forever. The expected value of this random variable, if I went ahead and integrated from 0 to infinity over this function with an X here, first of all, I'd have to do integration by parts, which isn't very fun, but I promise you it'll work out to be 1 over this parameter lambda. And if I wanted to get the variance of X, I'd actually have to do integration by parts twice for this term. Then I'd subtract the mean squared, and I promise you, if you like calculus, give it a try. And then you will get 1 over lambda squared. So if I take the square root of this, then I get the standard deviation. Now the CDF of X, that's pretty easy to develop. Recall, I'm going to put a little recall statement up here, that if I want to get the CDF, excuse me, and we know that for a continuous random variable, that is the probability my random variable is less than or equal to X. And for only continuous, it's less than X. And the way we get that for the range is we start with my lowest value of X, we integrate up to a general value of X under the PDF dx. And that's how we get a function in terms of X. So let's go ahead and do this. So the CDF of X, if I want to do it for the valid range here, I'm going to go from X is 0 to a general value of X of this function here. So we're going to go lambda e to the minus lambda x dx. And what you'll get is minus e to the minus lambda x here. Then you'll go from 0 to x. And then I promise you that this works out to be 1 minus e to the minus lambda x. So that's the general function when x is in range. So the prettier form here of this CDF looks like this, and it's more complete. Capital F, lowercase x, is equal to 0 whenever x is out of range, less than 0, and equals 1 minus e to the minus lambda x whenever x is bigger than 0 or in range. So let's take a look at an example here. This is a very common type of an example. The time until the next login, or the time between logins to computer systems, also the time between arrivals, tends to have this exponential distribution. So we have in this network, we have the time until the next login. It says it has the exponential PDF with a rate lambda equal to 25 logins per hour. So let's go ahead and show what we mean by this. So on a quiz or an exam, if you see this and then you see this, you should be able to say, oh, okay, my random variable X, which has a word definition, so that's what X is, the time until the next login. So we could say that this is the definition of X, the random variable. So we'd be able to say, oh, okay, lambda's 25, so we know that the general form is lambda e to the minus lambda x for x bigger than 0. So we should be able to reproduce that. We should also know then, we could write down a whole bunch of other things about this. Once we know lambda and we know it's exponential, then we know that the mean of this exponential random variable is 1 over lambda. So we know that that would be 1 log n every 25. But the rate is, it's 1 over lambda. So it means it would be 0.04 logins per hour. Is that right? No, that's not right. It's not a rate. I'm sorry. It's the time. It's time. It's 0.04 hours. Excuse me. 0.04 hours. I prefer it as 1/25 hours here. We would also know that the variance, that would be 1 over lambda squared. So we could just say 1 over 25 squared, and then that would be an hours squared. And then we could also say that the standard deviation is just also 0.04 hours, because we would take the square root of that. What they want to know here is, what is the probability that the time until the next login is between 2 and 3 minutes? So again, I put the definition of X here. I know what the PDF is, and also I know what the CDF is. I know that this is going to be 0 when X is less than 0, and it's going to be 1 minus E to the minus lambda X whenever X is bigger than 0. And again, remember what capital F of X is. It's the probability X is less than or equal to a specific value. So here's a plot of my time. So this is going to be in hours here. This is going to be F of X. And what they want to know here is to determine the probability that my random variable is between, now be careful here, 2 and 3 minutes. So that means you're either going to have to convert lambda to minutes, or you're going to have to convert these minutes to hours. And I prefer to just keep lambda as it is. So I know that 2 minutes is the same thing as 1 over 30 hours, right? Less than X, less than, in 3 minutes is 1 over 20 hours. So what they want me to figure out is, say this is 1/30. You could put this to decimal places if you'd like to too. But what we're trying to figure out here is this area that I'm going to shade in blue right there. So that's exactly what this area is right there. And we know that the area under the whole thing has to be 1. Okay, so there's a couple ways that we can do this. The first way we can do this is by simply integrating under this curve. So we can go X going from 1/30 to 1/20 of 25e to the minus 25x dx. We can do that. Or we can also, and I'll just tell you what that works out to be, okay? It'll be 0.1481. Or you can recognize that this probability of 1/30 to 1/20 is the same thing as saying capital F of 120, 1 over 20 minus capital F of 1 over 30. Why is that? Because capital F of 120, 1 over 20, I keep saying 120, is the probability my random variable is less than or equal to 1 over 20, minus the probability that my random variable X is less than or equal to 1 over 30. So if I color coded this and I said, okay, this is going to be this area right here. So that would be represented by this light blue highlighter marker there. And then the other area, use orange, capital F of 1 over 20, that would be all of this orange area, which is going to include that original dark blue area that I want. So I hope that you can see that if I take all the orange area and I subtract the light blue area, I get the dark blue area, which is what I want in the first place. So the reason I'm showing you both ways is sometimes it's like if you try to do this in your calculator, you may get an error. You try to divide by 1 and 20, and you can do this by hand, folks. It's not all that hard. You could easily have just done this and recognize that this is going to be minus e to the minus 25x, and then you're going to go x going from 1 over 30 to 1 over 20. I promise you that that's how you would do it by hand back in 1981 when I took calculus. Okay, so if we do this, and I use my plug and chug here, x is a 1 over 20. So that would be 1 minus e to the minus 25 times 1 over 20 minus, and then we'll have 1 minus e to the minus 25 times 1 over 30. And guess what? That's going to equal exactly what we got up here. It's the same thing. It's just a different way of showing it. So 0.1481. So you will see the exponential distribution for sure on the first exam, and certainly in quizzes as well. So probably in a quiz. Hope you have a good day.